Hi everyone, my name is Shahram Karami from L-Track Group at Monash University. This talk focuses on mechanism of formation of coherent structures in underexpanded supersonic impinging jets. Coherent structures are arguably the most important part in many fluid systems, especially shear flows. There are three mechanisms describing the formation of these coherent structures in shear flows. The first one is collective interaction. Low frequency acoustic wave forms a wavy shear layer. High frequency vortices are sitting on this low frequency motion, came together and form a large coherent structure. The other mechanism is vortex pairing. Vortices are formed in the shear layer, they roll, pair, and make a large coherent structure. Each pairing results in reduction in the frequency by a factor of 2. Another mechanism is spatial growth. The coherent structures form in the shear layer and exponentially grow in the shear layer. In this study, we use two frameworks of large-eddy simulation as a nonlinear unforced approach and local linear instability analysis to unravel the formation of mechanism of coherent structures in underexpanded supersonic impinging jets. We use an in-house code to perform a large-eddy simulation. If you are interested in the numerical methods, you can refer to this paper. We simulate two different cases with the same Reynolds number and nozzle pressure ratio, but different nozzle to wall distances. We utilize local linear stability analysis to study the evolution of almost unstable frequency in the streamwise direction. The flow is periodic in azimuthal direction. Assuming mean flow field is parallel, fluctuations can be presented as normal modes. Alpha and omega are complex numbers. M is the azimuthal mode number. Alpha, the real part, is the wavelength, minus imaginary part is the spatial growth rate. Omega, the real part, is the frequency, and the imaginary part is the temporal growth rate. If we introducing this normal mode into the linearized Navier-Stokes equation and simplifying, we will reach the compressible Rayleigh equations. In this study, we are interested in spatial growth. Then we consider omega being a real number. Let's look at some of the results. Large-eddy simulation. Let's look at the time scale of coherent structure in underexpanded impinging jets. We use the autocorrelation of radial velocity fluctuations sampled at the shear layer for two cases. As you can see in these two contour plots, the coherent structures or coherent motion start about 1 jet diameter from nozzle lip. Both cases have the dominant coherent structure, but the time scales are different. If we using triple decomposition, that means we decompose the flow field into mean, coherent part, and fluctuations, and calculate the time scale of fluctuations, what we see is the time scale of random fluctuation is an order of magnitude smaller than the dominant time scale of coherent structures. This gives us the indication that these coherent structures are dominant in this flow field. Let's revisit collective interaction mechanism. The autocorrelation of radial velocity fluctuations sampled at the shear layer shows that high frequencies are near to the nozzle, and then they converted to the low frequency coherent motion a jet diameter from nozzle lip. Then we do not see low frequency motion being dominated near to the nozzle. This gives us indication that the collective interaction is not the dominant mechanism in this flow. Let's look at the vortex pairing mechanism. In the original experiment by Winant and Browand, the length required for a successful pairing, non-dimensionalized by initial momentum thickness, is about 100. Considering the same condition is valid in our case, the length required for one successful pairing is 4 to 5 jet diameter. In addition to this one, we look at the animation of vorticity field. We observed occasionally pairing occurring, but at most we have two pairing, and these two pairing can reduce the frequency by a factor of 2 to 4, which gives us the indication that this mechanism is not the dominant mechanism of reducing the frequencies in the shear layer of this configuration. To study spatial growth using large-eddy simulation dataset, we define the energy of fluctuations in compressible flows, which also known as Mach energy, as follows. Define norm of energy of disturbances A, which is the function of a streamwise location, azimuthal mode number, and Strouhal number. What we did is first Fourier transform of energy in azimuthal direction and time, and then perform integration in radial direction. The integration should be in the radial domain limited to the shear layer. We located the center of shear layer at the maximum location of mean turbulent kinetic energy, and the radial limits are the radial location of the 5% of the mean turbulent kinetic energy centered at the center of the shear layer. These two contour plots showing the energy norm as a function of a Strouhal number and a spatial location for both cases of nozzle to wall distance of 2 and 5. As you can see, the Strouhal number of the maximum norm of energy as we moving in a streamwise direction is dropping by a factor of 4 to 8. This gives us the indication that the spatial growth is the mechanism dominant in this configuration. As also mentioned earlier, we utilize local linear stability analysis. We are interested in a spatial growth rate, then omega is a real number. At each axial locations, we have the mean field, substitute the incompressible Rayleigh equation, pick the frequency, solve the compressible Rayleigh equation to obtain the growth rate. Then we perform this analysis for a wide range of frequencies to obtain the growth rate as a function of frequency for each axial location. Do it for different axial locations for both cases, considering the most unstable frequency has the maximum growth rate at each axial location, and collecting this data, putting it in one graph, showing the most unstable frequency as a function of a streamwise location. What we see is most unstable frequencies for both cases drop by a factor of 8 in one jet diameter based on the local stability analysis. Now if we combine the findings from LES dataset and linear instability analysis, we will see they are in good agreement. This gives us indication that the spatial growth is the mechanism dominant in this configuration. This brings me to conclusion slide. We perform large-eddy simulation of underexpanded supersonic impinging jets. We use different techniques to obtain time scale, length scale, and velocity scale of coherent structure in the shear layer of the jet. We found that coherent structures are formed in one jet diameter from the nozzle. High frequencies are converted to low frequency motions. We roll out two mechanisms of collective interaction and vortex pairing. Utilizing the energy norm, we show the spatial growth is a mechanism of formation coherent structures. We also use the local instability analysis and reach to the same conclusion. Happy to take questions. If you watch this as a recorded seminar, please feel free to contact me on my email address.